This is the second lesson on ANOVA, lesson 12, part 2. And we're going to start with another example and kind of just work our way through this thing. Goal for this lesson, get more practice in with ANOVA just to feel comfortable with this thing in general. And then I also want to fine-tune some of the language so I'm more consistent with sort of industry standards. And as a final note, I also want to be able to use technology to do some of these tests and the follow-up test should I have to compare multiple groups. So here I have the daily tip amount for 3 different servers at different restaurants. I have Anna, Brent, and Charlie. These are in US dollars, so I have $24.35 and so on. If you are watching at home, what I would encourage you to do at this point is pause the video and see if you can find the average and standard deviation for Anna, Brent, and Charlie here. I'm going to use GeoGebra to come up with my values, and I'm also going to do that stacked box plot thing that we saw from last time. But all the same, pause your video and see what you can come up with. So I typed my stuff in GeoGebra. If you want to do this in GeoGebra as well, let me show you how this works. So I'm in spreadsheet. I've typed my data in spreadsheet, A, B, and C for Anna, Brent, and Charlie, just keeping that nice and easy. I select my data by clicking and highlighting it. And then I'm going to go to this thing that looks like a histogram, and I'm going to choose multiple variable analysis because I'm comparing more than one group. And there's Anna, Brent, and Charlie right there. I'm going to hit this thing right above where my video box is, and it gives me the show statistics. And down at the bottom, it's giving me the mean and the standard deviations for each of those groups. So Anna, $28.2 on average. Brent has an average of 21.82 if I round that thing. Charlie has an average of 33.77. Standard deviation for that first group. I'm assuming that these people can still work and get more tips at their jobs eventually. So I'm treating this as a sample because if this is a population, then there's no point in actually doing the analysis. I would know definitively which individual gets a better amount of tips on average. So I'm assuming that I'm treating this thing as a sample and I'm trying to predict over a long period of time who is actually getting a different amount of tips at these restaurants, if any difference at all. And I'm noticing that these all have different sample sizes. I have 10, 11, and 13. When I have different sample sizes, my math ends up being just a little bit messier than if it were all the same. If all the sample sizes were the same, it's called balanced. We'll see an example of balanced later in this lesson. A lot of the denominators end up being really, really clean. The averages that we're finding involve minimal to no work. We're going to have to do a bit more for this one. That's okay. I'm not going to close GeoGebra forever here because I'm going to revisit this thing when it comes to technology. So if you have GeoGebra open at home where you've typed in your data and you've chosen that box plot, I would leave this open. We're going to come back to it. I'm going to switch my view over to the packet though, and we're going to just do this problem using ANOVA from start to finish. So I'm switching my share. I'm going to zoom in and hopefully fix the autofocus so it's a tiny bit more readable. Okay. Step 1, we state the hypotheses. The null hypothesis is that all the averages are the same. The alternative hypothesis is that at least one of the averages is different. We found the variation between the groups by taking the weights times the individual averages minus this grand average. This grand average we could find in one of two ways. One way I can find it is by adding up literally all of the numbers and dividing it by the number of term. Or I can do a weighted average where I take the number of samples in the first group times the average plus the number of values in the second group times the average divided by the total number of terms. So this capital X bar, this is a weight of all of the values, a weighted average. This variation between groups, this was the amount of variation that was taken up by just normal deviation between that sample average and this large group average. It was how the centers of my boxes compared. Here are the centers of boxes. It's how all the centers of those boxes compared to this midline X bar. So this tells me how the centers are different, but it doesn't talk about the spread of those boxes. The spreads of the boxes was the variation within the group. This was my pooled variance. And I got this by taking a weighted average of all of those individual variances. To find my F ratio, I take the variation between the groups, the amount of spread that I've essentially taken, and I divide this by the variation within the groups. This is the amount of spread that I was allowed to take. There are 2 degrees of freedoms when working with this model. K minus 1, that's the denominator on that first set of values there. And capital N minus K, where capital N is the total number of values, is my second denominator, and it's my second degree of freedom. This has 2 degrees of freedom. One of these degrees of freedom is for the between, and one of them is for the within. Now, you might also see this referred to as the numerator and the denominator. That's fine as well. I have several assumptions for using this model. I need to have a random sample. By random, I mean there's no bias. I need to make sure that I have independence both within and between my groups. I need a large N. That was N greater than or equal to 30 or starts normal. These were all the same as a t-test. So these assumptions here, just think I have to have these whenever I compare averages. The last one I had was something about equal spread. This was that the standard deviations should be comparable. So if I had like a standard deviation of 3, another one of 5, and another one of 8, I'd be like, oh, 3, 5, and 8 are ballpark close to each other, I guess. It's not as bad as having 3 and 27,000. So as long as they're reasonably close, this distribution is somewhat forgiving. But this pooled variance assumes that I can kind of shove everything together and spread it out. So if they're not the same, I'm not allowed to do this type of calculation. I would have to try to determine a new model to do the analysis. This is always a right-tailed test. So when we look at this up in our calculator, it's going to be FCDF. Whatever we get for our F ratio or our F score or test statistics, those are all different names for the same thing. Comma infinity, because it goes to the right. First degree of freedom will be this K minus 1, number of groups minus 1. Second degree of freedom is the total number of terms minus the number of groups. So this K, this is equal to the number of groups. This N, this is equal to the number of values. And I want to do just a little bit of scratch work for what we got going on for this amount of money for tips. Just to make sure I'm okay with some of the terminology. First off, for tips, I had a K of 3 because I was looking at 3 people. If I added together the total number of values, I had 10, 11, and 13. I believe this gives me 21, 31, 34 days of tips between the three people, throughout the three set of people where I was recording their daily tip amount. So this gives me one of the degree of freedoms is going to be 2. The other degree of freedom is going to be 34 minus 3. The other one's going to be 31. Other thing I want to calculate is this capital X bar. So I can find this by taking all of those individual values that I had. So I can go back to my list of raw values and I can check, and I could do something like, well, the first number was 24 plus ... all the way to the last number was 41, and I had 34 values. So I could just add all of those things up. Or I could do a weighted average because I found those individual averages. No matter how I do this, I end up getting something like approximately 28.647 or so. I'm going to calculate the variation between, because I have the formula nearby and it's going to help to have the formula nearby. The number of values in the first group was 10. The first average was 28.2. I'm comparing that to 28.647 squared plus ... I would do the same thing for the next value. The next value, I had 11. I'll have 11 times 21.82 minus this 28.647 squared. I'll have 13 times 33.77 minus 28.647 squared. And I'm going to divide this by the number of groups minus 1. When I type this into my calculator, for the variation between groups, I get something like 425.54. I'm going to look at the variation within. This is my pooled variance. The formula I'm going to take for this is I'm going to take the degree of freedom for each of the groups and multiply it by the variance, which is the standard deviation squared. So I had 10 values in that first group. That's a DF of 9. My standard deviation was 3.82 squared, plus the next value had a degree of freedom of 10, plus 5.44 squared, plus ... That ... is just going to be the next value. DF is 12 times 3.56 squared. And I'm going to divide this by the total number of terms, 34, minus the number of groups, 3. All have a denominator of 31. And when I do this calculation and I type this into a calculator, I get approximately the variation within to be something like 18.70 or so. I'm going to put all these pieces together now and let's look at the test. So my first step is my hypotheses. My null hypothesis is going to be that all the averages are the same. Alternative hypothesis is that at least one average is different. Second step is model. And the model that I'm using is the F distribution. The name of the test, all 4 steps, is called ANOVA, but the model is called the F distribution. And my F, I'm going to find by taking the var between divided by the variation within. The variation between groups, I took 425.54 spread. The amount of spread I was allowed to reasonably take was 18, so it feels like I'm a little bit over budget. I'm going to divide this to figure out what my F ratio or test statistic is. and I get something like 22.76. This has 2 degrees of freedom. My first degree of freedom is for the groups. 3 minus 1 gives me the first degree of freedom is 2. My second degree of freedom was at 34 minus 3. That was a degree of freedom of 31. So my numerator degree of freedom is 2. My denominator degree of freedom is 31. As my third step, I'm going to calculate my p-value. My p-value is f/CDF. I start at 22.76. This thing goes forever in the infinity direction. The first degree of freedom is 2. The second degree of freedom is 31. I type this into a calculator and I end up getting a p-value of, not surprising, pretty much just straight up 0. It's really, really small. I'm going to show you how I got that p-value using my calculator again. So I went into second vars, or I'm going into StatList editor and I'm choosing F5 for distribution. I choose f/CDF. My low value, my high value is infinity. My first degree of freedom is 2. My second degree of freedom was 31. So this tells me I had 8e minus 7. This is scientific notation, so this means I have 0 point, and then I have 6 zeros, and then an 8. This is a really, really small number. When it's that small, I use this 0 plus kind of notation. As a final step conclusion, my p-value is less than pretty much any alpha that I could want to choose, so I reject the null hypothesis. I have evidence of a difference in those different tip mounts. Now, just because I have evidence of a difference, I kind of have a little bit of a lackluster conclusion there. I don't know which groups are different. So I don't know if it's A and B, A and C, B and C. I still have to do all of those comparisons thereafter, but at least I know it's worthwhile to do all of those extra tests, because if I would have failed to reject, then everything would look roughly the same to me. There would be no point in doing a follow-up. So this is the first of, we're going to do several examples of using ANOVA just to get one more under our belt, sort of feeling a little bit more confident. What I'd like to do now is improve the language a bit, because while we're using these phrases of variation between and variation within, these help me remember where these things are coming from. Industry standard uses language of treatment and error. So variation between. In a medical setting, this would be comparing a control group to medicine at a certain dosage to medicine at yet another dosage. So I'm comparing all these different treatments to see which one is the most effective. As a result, I call this whole thing some sort of comparison of treatments. Being more specific, when I look at this formula for the variance, I am adding all of these things that have been squared where it compares the treatment. So I'm looking at the sum, I'm adding together a whole bunch of square things of a whole bunch of treatments that are being compared. So I have the sum of the squares of the treatments. I abbreviate this as the sum of the squares of the treatment, SST, and I divide this by k minus 1. K minus 1 is my degree of freedom. When I do this division, I've taken this total and I'm dividing it by the number of terms in some sense. And when I take a total and I divide it by the number of terms, I actually calculate an average or a mean. So by dividing this total sum of the squares of the treatment by the degrees of freedom, we find something called the mean square of the treatment. So the average square value when I'm doing this comparison is the same thing as my variation between groups. It's the same thing as taking the SST divided by the degree of freedom. So the takeaway here is the term MST and variation between groups interchangeable. The variation within groups, this was based off of all of these standard errors. We've been calling them standard deviations for samples. So we've looked at the sum of all of these squared standard errors, the sum of the squared of the errors, the SSE. Now, likewise, when I divide this by the degree of freedom, I am taking a sum divided by some sort of a total. And by doing sum divided by total number of terms, this becomes an average. This is the mean for the squares of the error. We call this the MSE. And the MSE is the variation within groups, which is the same thing as my pooled variance. It's how much things are spread out. And I can see that this is a weighted average of all of these individual variances. It's a mean of the squares of the errors. It's a pooled variance. So the mean of the squares, this is really saying I am pooling together my data of the SSE divided by the degree of freedom. So MSE, that's another way of saying variation within. So I used to do variation between divided by variation within. Between is MST, within is MSE. So my F ratio is MST divided by MSE. I remember this as T is on the top, the MST is on the top of that F ratio. This is not new math, this is just new vocab, and we are going to practice this new vocab to get comfortable with it. Something you may have noticed in the previous problem, and if you didn't, I'm going to give it to you here as well. The degree of freedom for the numerator, or for the top of that fraction, on the last problem, my between groups was 2. And my degree of freedom for the denominator was 31. Now my total number of values was 34. When I add these, 2 and 31 gave me a total degree of freedom of 33, which in a sense is really just n minus 1, which is sort of the ideal degree of freedom. It's an overall degree of freedom when I pool together all of my values. So my degree of freedom total is always going to be found by taking the total number of values minus 1, or you can think of your group being split up between these two types of spreads. I have spreads within and I have spreads between. So I'm going to take all of this vocab right now. You're seeing it for the first time. It's like learning a new language. So it's almost like I've given you 5 new words in a different language and I said, memorize these things. That's not practical. So we got to practice these so we can get this into our heads a bit. So here's a table where we can practice this a little bit. And I'm just going to write some notes to myself, like little mini flashcards at the top of the page, so I can try to remember things a little bit better. The variation between groups, this was the same thing as the mean square of the treatments between compared to the treatments. I found this by taking the sum of all of the squares of the treatments, and I divided this by the degree of freedom for the treatments. The var within. This is my pooled variance. I found my pooled variance by finding the average of each of my individual variances. So I was looking at the total sum of the squares of those standard errors, the sums of all of those variances, and then I averaged this out based off of the degree of freedom for that second group, or second set of variation. So looking at this together here, I have a small ANOVA table, and when we're using technology, we're going to get a bunch of printouts that look something like this. Let's see if we can figure out what this table is telling me before I calculate anything. So this is a new set of values, and it gives me a row here for treatment. So this is telling me something about the between. And it gives me a row here for the air. This is telling me something about the within. So where I see this df, this is the degree of freedom for the treatment. This is the degree of freedom between groups. So one of my degrees of freedom here was 2. My second degree of freedom for the within group, for the MSE, that was 24. So this is giving me what each of those degrees of freedom will be when I'm doing some mini calculations. SS stands for the sum of the squares, so this is the sum of the squares for the treatment. This is my SST. This is the sum of the squares for the airs. This is my SSE. So if I was thinking of what this would look like as a hypothesis test here, first step, I would have my null and alternative hypothesis. First thing I might be curious is, how many groups do I have? Well, the degree of freedom between my groups for the treatment is the number of groups minus 1. And this formula up here is saying that's 2. So this is telling me that the number of groups must have been 3. 3 minus 1 gives me 2. So I am going to be comparing an average for the first group, an average of the second group, and an average for a third group. My alternative hypothesis is going to be at least one of these averages is different. I'm comparing multiple averages, so I'm going to do so using an F model. I'm going to calculate this F model by taking my variation between and dividing this by the variation within. Using this new language, I'm going to take the mean squares of the treatment, and I'm going to divide this by the mean squares of the air. I'm going to go back and I'm going to calculate what these values are to do that comparison. But once I have these values, I'm going to find my p-value by doing FCDF. Whatever this number ends up being, comma, infinity, it's always a right-tailed test, comma, my first degree of freedom, comma, my second degree of freedom. I can actually see these degrees of freedom already. First degree of freedom is 2. Second degree of freedom is 24. So I'm well on my way to finding this p-value. I need to find these MST and MSE numbers to calculate my F ratio. Let's do that now. MST. This is the variation between groups. I'm going to take the SST, the sum of the squares of the treatment, and I'm going to divide this by the degree of freedom for the treatment. So I'm going to take 28.22, and I'm going to divide this by the degree of freedom there was 2. When I do this division, I think I end up getting 14.11 as that first MST number for my variation between groups. Let's calculate the MSE. I'm going to take the sum of the squares of the airs, and I'm going to divide that by its degree of freedom. The sum of the squares of the air, this was 28.44. The degree of freedom for that second group was 24. When I'm saying group there, I mean source of variation. And I got 1.185 or so. So filling in my table a little bit, my MS for the first was 14.11. My MS for the second was 1.185. my F stat, or my F ratio, when I do 14.11 divided by 1.185, gives me something of about 11.91 or so. This is large. Anything bigger than 1 is large. 1 represents taking 100% of your variation. Here I've taken 1,191% of my variation. This is so big that I'm expecting to get a very small p-value. Let's check. I'm doing second vars. I'm doing FCDF. I'm doing 11.91 comma infinity, 2, and 24. And this is giving me 2, or if I round this thing 3, e minus 4. So this means I have 1, 2, 3 zeros after the decimal place, and then a 3, up to a little bit of rounding. So my p-value here is very, very small. So for my conclusion, since my p-value is smaller than something like a neutral alpha level, I would reject the null hypothesis. If I'm rejecting the null hypothesis, I have evidence of a difference in those averages. It doesn't say which averages are different, and actually with the table that I'm provided, I don't even know what the average was for the first, second, and third group, but I do have my conclusion of the test. I am able to fill in this partial table, and I got to practice this new language a bit. MST, this was the between. MSE, this was the within. I'm going to show you how to calculate the MST and MSE for our data that we started out with for the tip amount there. And I'm going to start by going into GeoGebra just to show you what that process looks like. And then I'm going to show you again using graphing calculators. Let's start with GeoGebra first, though. So I'm inside of GeoGebra. I have all of those individual values for the daily tip amount for Anna, Brent, and Charlie. And down here I have my statistics. Where it says statistics, if you click that box, it'll actually give you an option for a whole bunch of other tests. Go ahead, and if you're following along in GeoGebra, see if you can find the option that says ANOVA. I'll give you a second to try to find that. I'm going to click this here in just a second, and I want to see how this lets me compare groups A, B, and C. And I'm going to compare this to the first page of this note packet just to see how close my values actually are. GeoGebra is using the language of DF, SS, MS, F, and P. So this looks a lot like that table that we just did there, but it's using this language of between and within as well. I'm going to write down these numbers that I'm getting from this table, and I just want to compare this to what we had from earlier. So I'm making a very short copy of this table. I had between, I had within, I have the DFs they're giving me are 2 and 31 with a total of 33. I had an SS of 851.0736. I had an SS of 579.5441. I had an MS of 425.5368. And an MS of 18.695, an F of 22.7621, and finally a p-value of 0. I'm just transcribing this table, and I'm going to pull this table back up, and let's look at it, and let's compare what GeoGebra is saying to what we got from earlier. So I'm going to share my packet with you. This is the same table that I just had in GeoGebra. And from this, I'm going to see how things match up. Well, first note, to get any of these MS values, it's pretty easy to check if these things look reasonable for your table, because to get an MS, you take your SS divided by your DF. So if I take this 851.7036 divided by 2, I'm getting this 425 number. That looks great. 579.5441 divided by 31. This is giving me this 18.695 number. I can see that both of these MS things look good. Now, when we did this calculation earlier for the variation between groups, I got 425.54. Looking at my grid here, my MS for my between, my MS for the treatments was also 425.54. I've just verified one of those numbers. Likewise, when I set up that fraction to find it, my denominator was 3 minus 1, so my degree of freedom for this was 2, and that also matches what I'm getting with GeoGebra. Looking at the variation within, my variation within, when I did it by hand, I had this long calculation where I was dividing by 31, and it gave me 18.7. So I had 18.7 with the degree of freedom of 31. Looking at this table, my mean square of my within, my mean square of my errors was 18.7. My degree of freedom for the within was 31. My by hand results and my calculator results are matching up. If I divided my MST by my MSE, so I'm just going to divide these two numbers. I'm going to divide these two numbers to the same numbers. And I hit enter, dividing 425.54 divided by 18.7. I end up getting something like 22.76 or so, which again is matching up with the table. It's giving me an F score of 22.76. So GeoGebra is an excellent way to double check my work to make sure I'm doing these longer calculations correctly. GeoGebra is also really nice because it's kind of this in between where it's using some of the industry language of SS and MS, but it's also using the more conceptual definitions of between and within. So that way I know where stuff is coming from, if it's the treatments or if it's coming from those standard errors. What I'd like to do now is also show you how to do this stuff in your calculator to give you yet another resource to double check your work. So I'm going to go inside of my TI-84. And while I'm inside of my TI-84, I'm going to type in all of my data into my calculator. Let me show you what that process is going to look like. So in my calculator, I'm going to flip this page over. I'm going to go stat. I'm going to choose the option for edit, and then I'm going to type in all of my data. So stat, first thing says edit. In list 1, I'm going to type all of the amounts that I had for Anna. I had 24, I had 35, 28, 29, 32, 25, 25, 28, 24, and 32. I'm going to try turning on a light and seeing if that makes that easier to read. It does. Great. For the second list, I had 24, 28, 23, 31, 14, 17, 22, 22, 24, 13, and 22. And now I'm going to type in all this information that I have for Charlie. After I've typed in all the information into my calculator, my next step is I'm going to go stat, test, and I'm going to choose ANOVA. Now, if you're doing this at home, I just want to give you a little bit of time to type this into your calculator. So I'm going to leave this up for you to type in for just a second. And I'm going to type the same thing into my TI-89 just to make sure I can do this in both of my calculators. So my 89, I'm going apps. I'm going into the option for stat list editor. And in that first list, if I choose the top of a list and I hit clear and enter, it will clear the list for me. So I'm just clearing these lists. In list 1, I'm going to type all this information for Anna. For the second list, I'm going to type in all the information for Brent. Next group, I'm going to type in all of my information for Charlie. And giving you a second to catch up. Oh, and it looks like I left off a couple numbers. It looks like I left off the 24. I'm going to add that. 24 and the 33. Double checking the sample size, 8, 9, and 11. Great. That's a good thing to do. When you're done typing in your data, make sure that it matches up with what you're counting by hand. I noticed that my count did not match up. That's because I was missing the first row of values. Easy to fix. I just typed those in and I added them. I'm going to do ANOVA and the TI-84 first. So I'm going to hit the stat button that's right underneath delete. I'm going to hit the over arrow until I get into test. And I'm going to scroll down until I see the option that says ANOVA. That's way down on the bottom. Now on my calculator, list 1, list 2, list 3, these things show up in the bottom in blue. So I'm going to hit blue and then 1. And when I do this, it's going to say I'm using data from list 1. I'm going to hit the comma button. The comma is above the 7. And I'm going to do blue 2 for list 2, comma blue 3 for list 3. My values are in list 1, list 2, and list 3. And that's all there is to it. I'm going to hit enter. And this is going to give me my F of 22.76, a p-value of 0 plus, a DF as a factor, factor means treatment, of 2, an SS, an MS, and then I have some stuff for the air down below. Great, I'm going to write down all of this information here into my packet in just a second, but I want to show you how to do this in your TI-89 as well. In your TI-89, tests are up top here where it says F6. A couple ways to get to F6. You can do blue and then this button that says F6, or you can just do F5 and hit the over arrow a couple of times until you're in that right menu. Inside of F6, I'm going to scroll until I see something about ANOVA. I see ANOVA showing up here. It's going to ask me if I have raw data. I do, so I'm going to choose data. It's going to ask me for the number of groups. I have 3 groups. It's going to ask me where my first list is. In order to have list show up on the TI-89, it's in the variable link button. So I'm hitting blue, and then I'm hitting the minus button on my calculator. I'm going to choose list 1 as my first list. Blue, minus button, I choose list 2. Blue, variable link, I'm choosing list 3. I hit enter. It's giving me my F, my factor, and it's giving me my error information. So the same thing I had in my TI-84. Now my TI-84 print is a little bit brighter, a little bit bigger, and a little bit easier for me to read. So I'm going to use this, but let's write what we got from our calculator down at the bottom. First thing, when it's talking about factor, factor is the same thing as treatment. So it gave me a mean square of the treatment at MST of 425.54. This is the same thing we got by hand. This is the same thing we got in GeoGebra. Scrolling down, the mean square of the errors was 18.69. Again, same thing in GeoGebra, same thing by hand. We've now done the same problem 3 ways. F is that top number, 22.76. P-value, I have 8e minus 7. That's scientific notation, so this means I have 1, 2, 3, 4, 5, 6 zeros, and then an 8. We just were calling this 0 plus because it was so small. And my calculator gives me one more thing that's kind of interesting. Down at the bottom is giving me this SXP. That SXP is really your pooled standard deviation. Now your pooled standard deviation here is telling you roughly what would happen if you kind of shoved all of your groups together and you found sort of this average standard deviation for all of those values. Now, just as a note, if we square this number, let's see what happens. So I'm kind of squaring up those standard errors that I've been adding together. And then I've kind of averaged it out in some sense. This gives me, when I square 4.3238, 18.69 or so, which a quick verify is giving me the MSE. So when your calculator is giving you the pooled standard error, one way you can double check this is the square root of the mean square of your errors should roughly be what your standard deviation looks like for the entirety of your set. We've done another example of looking at ANOVA from scratch. We've done an example with totally different numbers where we've done ANOVA with a partial table. We came up with the table in GeoGebra. We came up with the values in the calculator. There are a few things that I have left to deal with. One of those things is I can clearly see that my p-value is low and I'm rejecting the null hypothesis in this problem. This told me I had evidence that there is a difference in those 3 groups, but I still don't know what to do about that. So if I wanted to compare groups for the tip amount, I would have to compare Anna and Brent. I would have to compare Anna and Charlie, and I'd have to compare Brent and Charlie. So I'm listing out every letter combination I can possibly think of for side-by-side analysis. And in this case, when I do this, I'm noticing that I end up with 3 pairs of tests that I'll need to do. So if I just had an alpha of 5% for each of these tests, well, my error would add up with repeated tests. So this would really be like a 5% error for the first, another 5% error for the possible second, and another possible 5% error for the third. So my total error blooms considerably, and I'd be looking at a total possible error that I'd be comfortable with of 15%. That's not what I really want. I want to end at 5%. So what I want to do here is I want to correct what each of these tests should be in order to add up to 5%. So we want to split this alpha for the number of pairs that we're dealing with. So I had 1, 2, 3 pairs. I was using an alpha of 5%. So I'm taking this 5%, I'm splitting it up 3 times. If I was following this thing up with a whole bunch of hypothesis test for A and B, a test for A and C, and a test for B and C, I would want to use an alpha level of 0.016 repeating. I'm splitting that into 3. This process of just dividing the errors, not complicated enough to seem like it warrants a name, but it does have a name. This is called the Bonferroni Air Adjustment. And all you're doing is you are taking the alpha and you're dividing it by however many follow-up tests that you need to do. If instead of a test you wanted to do a confidence interval, well, your confidence interval for a follow-up is going to be 1 minus your corrected alpha level. So for example, I would have an alpha level of 1.66 repeating, but if I wanted to do confidence intervals instead for looking at the difference, I would be working with something like 0.98.33 repeating percent for each of those comparisons. So Bonferroni just takes that total error and it splits it up depending on how many groups you want to be comparing. I've got all of this data typed into my calculator already for Anna, Brent, and Charlie. And just as a reminder, in list 1, I had all of the data for Anna. In list 2, I had all of my information for Brent. And in list 3, I had all of my information for Charlie. So if I wanted to compare these things 2 at a time, A to B, A and C, and B and C, I am going to go through this process, and to do this, I'm going to use 2 sample, because I'm looking at 2 samples in each of these, A and B, A and C, and B and C. That's 2 groups at a time. 2 sample t-test to do that comparison. And I can do 2 sample t-test using either GeoGebra or a calculator. I'm going to use a calculator. I could also do it by hand. There's a lesson packet that goes over the process for doing it by hand. I'm feeling a little bit lazy, so I'm going to do calculator though. And for each of these things, I'm testing the alternative that the 2 groups are different. The null hypothesis is that the groups are the same. So first test I'm doing, I'm comparing Anna and Brent. In my calculator, I'm going back to where I saw my test. So stat test, or stat list editor, and I'm choosing F6 for test. And I'm choosing a 2 sample, because I'm looking at 2 samples, and I'm doing a t-test. It asks if I have stats or data. I actually have the data. Remember, I have all of this thing typed into list 1, list 2, and list 3 already. I'm going to compare Anna and Brent, so I'm comparing list 1, L1, and L2. This looks good so far. For alternative hypothesis, I'm testing for a difference. When I am doing ANOVA, I had that pooled variance, so I'm going to pool. If I don't pool, it's not going to make that big of a difference. I'll show you the two things side by side here. And I'm going to go down to where it says calculate. When I do this, it gives me a t-score of 3.08, and it gives me a p-value of 0.006. I'm going to do the same thing again with you, and I'm just going to show you what it looks like if I choose no pooling instead of pooling. Instead of a p-value of 0.006, I end up with one at 0.0057 rounded up 0.006. So even if you choose the option of no pooling, you'll get the same results. ANOVA, you pool though, so to be consistent, it's probably better if you pool again. So 0.006. Now, when I'm doing the conclusion, I'm not going to compare this to my alpha of 5%. I'm going to be doing a lot of tests, so I need to compare this to my corrected alpha level of 1.6%. Well, 0.6% is less than 1.6%, so this means I reject the null hypothesis, which means I have evidence of a difference between groups A and B. So A and B, this is one group that appears to have a difference in those averages. Anna and Brent appeared to have a different amount that they got in their daily tip amount. Well, let's check out Anna and Charlie now. Anna's in list 1, Charlie is in list 3. Alternative hypothesis, I'm wondering if Anna and Charlie make a different amount. So I'm going stat, test, 2-sample t-test, first list for Anna, second 3, third list for Charlie. I'm leaving everything else alone. I'm going to calculate. And I got a p-value of 0.0017 or so. This is also small compared to my corrected alpha star of 1.6%. So again, I'm rejecting the null hypothesis. I have evidence of a difference between groups A and C as well. If you're following along at home, please pause the video and I want you to compare Brent and Charlie, that second list and the third list. Does there appear to be a difference between Brent and Charlie? And let's check. Average for Brent, average for Charlie, stat, I am doing a test, I am comparing, second 2, so second list Brent, third list Charlie. I'm going down to calculate, and I get a p-value of 2e minus 6. I'm calling that 0 plus. That's 5 zeros and then a 2. That's a really, really small p-value. My p-value is smaller than my corrected alpha level for all of these things. So that told me that Anna and Brent were getting a different amount. Anna and Charlie were likely getting a different amount, and Brent and Charlie. So it wasn't just one that was different, They're all different here. That's not always the case. So the alternative hypothesis is that at least one is different. Sometimes we end up with multiple groups being different. We've now seen how to do the test by hand, calculator, GeoGebra. We fine-tuned the language with MST and MSE, and we did the follow-up with these 2x2 little two-sample t-test, and we corrected our alpha level using the Bonferroni Air Adjustment. Let's do just one more example of a test from start to finish, just to kind of see what things look like. And I want to do example 7 here. And there's more than one way to do this problem. But you want to compare two routes for getting to work. Route 1 takes 30 minutes on average with the standard deviation of 15 minutes. And I did 100 samples for Route 1. Route 2, 25 minutes on average with the standard deviation of 10, and also 100 samples. So I have the same number of samples for both. When this happens, when you have something like 100 and 100 where everything is nice and even, we call it balanced. Compare the averages using ANOVA. Okay. So 4-step process. First step is I have my hypotheses. I'm wondering if route 1 on average takes the same time as route 2. Alternative hypothesis, I'm wondering if at least one is different. If I only have two groups, though, that's going to mean the two things are not the same. Step 2, my model is going to be this F distribution. F distribution has 2 degrees of freedom. First degree of freedom is the number of groups minus 1. The second degree of freedom is the total number of terms minus the number of groups. I have 2 groups, so 2 minus 1 gives me 1 for one of my degrees of freedom. I have 100 and 100. I have 200 values. I have 2 groups. So my second degree of freedom is going to be 198. I'm just going to do a tiny bit of scratch work here before doing longer calculations. So for the scratch, I want to find the overall average. And something that's really nice about this thing being balanced is when I say there were 100 values for that first average of 30 and 100 values for that second average of 25 out of those 200 values, well, I have the same number of values in each. So what I can really do here is I can just take those two averages, 30 and 25, and I can truly just split them up by dividing it by 2. So when it's balanced, these longer calculations get really condensed in a hurry, and they get easier for me to do. So for example, halfway between 30 and 25, my capital X bar should be 27.5. I didn't even need a calculator for that one. Usually I need a calculator for these things. I'm going to calculate my variation between groups. And the way I'm going to calculate the variation between groups is this is my MST. I am going to add the number of values in each of the groups. I'm going to subtract the individual averages by the overall average, and I'm going to square them. So I'm looking at the sum of all of those squares, the SST, and I'm going to divide this by the number of groups minus 1. I'm going to divide this sum of the squares of the treatment by my degree of freedom. I had 100 values in the first group. First average was 30, minus the overall average was 27.5, squared, plus the second number of groups was 100, They had an average of 25 minus 27.5 squared. So I have the sum of the squares of the treatment, and I'm going to divide this by the number of groups, take away 1. Oh, 2 minus 1 is just 1. I could not ask for better numbers for this problem. So my MST, my variation between, I'm going to type this into a calculator and I'm going to see what I get. I have 100 times 30 minus 27.5 squared plus 100 times 25 minus 27.5 squared. And I end up with an MST of 1250. We're going to find the variation within. This is my MSE. I'm going to take the sum of the squares of my standard errors, and I'm going to divide this by the degree of freedom for the standard errors. So the way I'm going to do this is I'm going to look at the sum of each of those degrees of freedom times each of those standard deviation squareds, and I'm going to divide this by the total number of terms minus the number of groups. I had 100 samples in the first group, so I had a DF of 99. My first standard deviation was 15, so my variance is 15 squared. I had 100 in the second group, so a DF of 99. My standard deviation was 10, so my standard deviation squared is 10 squared. And I'm dividing this by the total number of terms, 200. Take away 2 gives me 198 in that denominator. Now just a note, since these are the same, if I divided everything by 99, what's really going on here for this MSE is I actually have 15 squared plus 10 squared divided by 2 if I divided everything by 99. In other words, I am averaging out my two variances here. I am pooling my variance when I do the MSE. And it's easy to see in this case that I'm averaging these things out when I happen to have exactly the same sample size. When I have the same sample size, it's called balanced, and in general, my math just ends up being a little bit clearer. I'm going to ignore example 8 here, and instead I'm going to keep going with this calculation. Reviewing what I have so far, I have an MST of 1250. I have an MSE of 162.5. So I spent 1,250 of my variation, and I was allowed to spend 162.5. It feels like I'm over budget a little bit. My F ratio is my MST divided by my MSE. When I do this division, 1250 divided by 162.5, I get an F of about 7.6923 or so. Third step, p-value. This is always a right-tailed test, so my p-value is going to be FCDF. Whatever my F-score is, infinity, whatever my first degree of freedom is, k minus 1, whatever my second degree of freedom is, capital N minus k. So I'm going to have FCDF. My ratio was 7.6923, comma infinity. My first degree of freedom was 1. That showed up as my first denominator. It's also 2 minus 1. My second degree of freedom, my second denominator was originally 198. I got that by doing 200 minus 2. I type this into a calculator. I'm doing FCDF 7.6923. I have degree of freedom of 1. I have degree of freedom of 198. And when I do this, I get something like 0.006 or so. Final step, conclusion. My p-value is low. If my p-value is low, my null must go. I reject the null hypothesis that the average time for the two routes are the same. I have evidence that the two routes are not the same. In other words, are different on average. I'm only comparing two groups, so we had an old way of doing this problem as well. I could have done the same thing using a two-sample t-test where I'm comparing those two averages. I'm going to use my calculator just to show you what I get when I did the two-sample t-test instead of doing ANOVA. I'm going to write down what I end up getting for my t-score, and I'm going to end up writing down what I get for my p-value. So in my calculator, I'm going stat, test, two-sample t-test, and I'm doing this from the statistics that I've been given for this problem. Average of 30, standard deviation of 15, 100 samples for that first group. Second group, I had an average of 25, the standard deviation of 10, and I had 100 for that second group. I'm testing for a difference. I do want to pool, and I'm choosing calculate. I end up getting a t-score there of 2.7735. I end up with a p-value of 0.006. So all roads lead to Damascus here. I have 2.7735, I have 7.6923. I have different t-scores and f-scores, but I still end up with the same p-value, 0.006. Previously, this is a note inside of a note, this is a note squared. When I took z-scores and I squared them, I ended up getting chi-squared. I'm curious if the same relationship might exist here. So let's see what happens when I take this t-score, 2.7735, and I square my t-score. Well, I end up getting 7.6923. So actually, I have the same relationship between t-scores and this f distribution. Here's what this tells me. Almost any problem that you can solve using z-scores with a hypothesis test, you can probably actually do that thing using chi-squared instead. Almost anything that you did using a two-sample t-test, you could probably get away with using an f distribution instead. F is the extension of t, chi-squared is the extension of z. These are the models that look at multiple groups. These were the models that we used for just looking at one group at a time. My point is, as you move on in your statistical career, you're going to find that you have options. If one of these models, chi-squared or z, is easier for you, then use the model that you find fastest and easiest. I personally find chi-squared to be easier than z, and I find t to be easier than f. That's just me personally. You might have different setups that you find to be your favorite, and I'm going to encourage that you practice those methods that you like, but also be comfortable with the ones that you do not like, because that's how you grow as a mathematician, is you practice the things that you're weak at until you're no longer weak at them. And you might find that your favorites change as you practice more. For example, I originally liked z-scores, but once I did a whole bunch of stuff with chi-squared, I'm like, oh man, this might have been strange at first, but this long term was much, much faster for me. Maybe the same thing is true for f and t for you. This finishes up lesson 12, comparing multiple averages using ANOVA. There's one more lesson that we're going to be looking at. Lesson 13 will compare linear regression, where I'm comparing several points. There's the relationship between ANOVA and linear regression. We likely will not be covering that, but if you're curious, feel free to send me an email or talk to me. I'd love to tell you about the relationship between ANOVA and linear regression.